Let's jump right in. Today, we're unpacking the mind-bending reality behind one of sci-fi's all-time favorite tropes. We're talking actual physics, some absolutely wild recent experiments, and a groundbreaking new frontier that honestly sounds like pure magic, but I promise you, it's 100% real science. So let's address the elephant in the room, the question we all secretly want the answer to. Can we actually pull a Star Trek and beam people up? When we hear the word teleportation, it's super easy to just picture Captain Kirk dissolving into sparkly lights on a transporter pad, right? But the reality of what physicists are pulling off today, it's weirder and in many ways infinitely more fascinating. We're going to separate the Hollywood myths from the quantum reality based on some incredible recent breakthroughs. Here's our roadmap for this explainer. We'll start with sci-fi versus quantum reality, check out the magic of quantum entanglement, and break down a record-breaking space teleportation. Then we'll get into the really crazy stuff, teleporting energy through a vacuum, before wrapping up with the future of quantum tech. All right, part one, sci-fi versus quantum reality. See, sci-fi teleportation is all about moving physical chunks of matter, literal atoms and molecules, from point A to point B. But quantum teleportation? Totally different ballgame. We aren't moving physical atoms at all. Because of something called the no-cloning theorem in quantum mechanics, you literally can't just copy a state perfectly. Instead, the process actually destroys the original state to build a flawless, distant copy. You aren't FedExing the object, you're sending its exact quantum blueprint and rebuilding it from scratch on the other side. And you know, this field is moving astonishingly fast. Back in 1935, Albert Einstein and his colleagues first proposed the theoretical paradox behind all this, and it sat as pure theory for decades. But fast forward to 1997, scientists in Innsbruck successfully teleported a photon's quantum state about a meter. Not bad, right? Well, by 2012, researchers hit 97 kilometers. And in 2017, we literally took it to orbit. From a chalkboard thought experiment to actual space in less than a century. Moving to part two, the magic of quantum entanglement. Okay, so quantum entanglement happens when two or more particles become so deeply linked that whatever happens to one instantly affects the other. And distance? Completely irrelevant. They could be sitting on the same lab bench or hanging out on opposite ends of the universe. Einstein famously hated this concept. He called it spooky action at a distance. But spooky or not, it is a verified fundamental rule of our universe. So how do scientists actually use this spooky action? Let's use the classic Alice and Bob setup. Imagine Alice and Bob share an entangled pair of photons. Alice keeps hers, Bob takes his far, far away. Now Alice has a third photon that she wants to teleport. What she does is measure this third photon together with her entangled one, which permanently links them. She then shoots the results of that measurement over to Bob using just a normal radio signal. Bob takes that data, performs a quick operation on his photon, and boom, it instantly takes on the exact quantum state of Alice's original. The original is gone, and Bob is holding a perfect copy. Which brings us to part three, record-breaking space teleportation. 870. That staggering number is miles. A team of Chinese scientists pulled off a massive modern breakthrough when they beamed the quantum state of a photon from a ground station in Tibet all the way to the Messias satellite orbiting 870 miles straight up. Just to put that into perspective for you, if they tried to do this using standard fiber optic cables, the interference from random heat and vibrations would be so intense, it would literally take 380 billion years to get a measurement. By bypassing the ground and shooting it straight up into the vacuum of space, they absolutely shattered existing distance records. Now, don't get me wrong, this experiment is incredibly tough to do. Entangled photons are remarkably fragile. If they bump into pretty much anything in the atmosphere on their way up, their state gets prematurely observed, and the teleportation totally fails. Out of millions of photons fired up from Tibet, only 911 actually survived the trip to be reliably received. It's kind of like chucking millions of messages in bottles into a Category 5 hurricane and somehow catching a few hundred perfectly intact on the other shore. To really wrap our heads around this, we need a complete paradigm shift. Bill Munro, a senior researcher over at NTT, hit the nail on the head. He said, "There's no matter, only information." That's hard to get your head around. And he's absolutely right. We aren't launching tiny physical balls of light into orbit. We are transmitting the fundamental underlying code of reality itself. Let's look at part four, teleporting energy through a vacuum. Okay, so this is where things get truly wild. Over 15 years ago, Theoretical physicist Masahiro Hata proposed a pretty mind-blowing fact. The vacuum of space is never actually empty. Even in a complete vacuum, quantum fields have these zero-point energy fluctuations, which means they carry an infinite amount of quantum entanglement. Hata theorized, hey, if space itself is already entangled, couldn't we use that invisible background network to teleport actual energy from one place to another? For a long time, that sounded like pure science fiction. But recently, a team led by space-time engineer Eduardo Martín Martínez actually pulled it off. They used nuclear magnetic resonance on an organic polymer molecule to essentially simulate this quantum vacuum. First, they entangled carbon atoms inside the molecule. Then, they fired a very finely tuned radio pulse to transfer that state to an intermediary messenger atom. Armed with that information, they were able to extract local zero-point energy right out of the destination atom. By breaking what physicists call strong local passivity, they quite literally pulled energy out of thin air. Well, out of the entangled network, to be exact. And the results were just jaw-dropping. If you just let energy travel naturally down that atomic chain, it takes roughly 700 milliseconds. But when they used the Quantum Energy Teleportation Protocol, the whole thing took 37 milliseconds tops. We are talking nearly 20 times faster than classical energy transfer. The energy didn't just travel through the molecule, it was instantly extracted from the local vacuum itself. And here's the kicker. This isn't just some abstract theory locked away in a single billion-dollar lab. Shortly after that experiment, a researcher named Kazuki Ikeda actually verified quantum energy teleportation using IBM's publicly available cloud quantum computers. He wrote the exact quantum circuits needed for the protocol. This means that literally anyone watching this explainer right now could theoretically log onto IBM's cloud and verify energy teleportation from their laptop. The future is literally already here. Finally, part 5, the future of quantum tech. So, what does this all mean for us? Let's rapid fire some practical applications, because merely observing a quantum state permanently alters it. A quantum internet would be physically unhackable. If anyone tries to snoop on your data, the entanglement instantly breaks and you know right away the line is tapped. Beyond that, we're looking at deep space communication, where data doesn't even have to physically travel. We're looking at advanced quantum computers solving problems in seconds that would take our best supercomputers thousands of years. And perhaps most incredibly, we're looking at the very first steps toward a global, instantaneous energy distribution network. Now, right now, teleporting energy does have strict distance limits, but Hata's research points to a genius workaround called squeezed vacuum states. Basically, by abruptly expanding space and stretching out those quantum fluctuations, you could maintain that zero energy correlation over massive distances. This could pave the way for a true global quantum energy network. Imagine a world where energy isn't just piped through massive copper wires, but is accessed locally, anywhere on Earth, or even on Mars, through the entanglement of the vacuum itself. So I want to leave you with a final thought to chew on. For all of human history, we've looked up into the empty vacuum of space and seen exactly that, just a whole lot of nothingness. But today, science is proving that space is actually teeming with an entangled web of limitless potential. If we can pull real, usable energy from the vacuum of space using nothing but quantum information, what else is hiding in the nothingness all around us? Thanks for tuning into this explainer, and keep questioning the reality you see.